So last time we just started section 2 of this unit, algebra of events, uh, or Boolean algebra. We just introduced the definition of sample space and events. So a sample space includes points, and the event is just subset of the sample space. Sample space just includes all the outcomes of experiments, and the event is just a subset of it. So we can define the probability based on sets. And we are all familiar with that. And we can do a lot of things with sets. We can do union, we can do intersection, we can do implement, we can do a lot of things. Those are the algebra for sets. But if you compare the algebra for sets and algebra for numbers or real numbers, then you can see some of them are really similar. If you, for example, consider union as addition of numbers, union of sets as addition of numbers, and intersection of sets as multiplication, then you can see the formulas or the laws for the numbers also work for sets. And so there's a correspondence, between the algebra in real numbers and the Boolean algebra. Especially the commutative and associative properties. Actually, as well as the distributive property also holds. So, for example, we know A union B is the same as B union A. If you change the union as the plus and change A and B to numbers, you can see that the equality still holds. Or if you change intersection as multiplication, you can see two numbers multiplied together. Really doesn't matter which one you read first. Okay, so there are commutative and associative. Like if you add three numbers, it really doesn't matter which ones you add first. Similarly, in the sets, you can take the union of any two sets, and then take the union with the other set, and the same for intersection. So that makes a lot of interesting properties, and we can actually use that kind of algebra when we simplify the Boolean algebra, as we're going to discuss some examples. For distributive property, okay, we just discussed commutative and associative property, but for distributive property, we know A intersect with B union C is actually the union of A intersect B and A intersecting C. And this can be easily proved by that Venn diagram on the next page. But if you try, change the intersection as multiplication and the union as addition, then the equation becomes A times parentheses B plus C equals A times B plus A times C. So that's exactly what it says in the distributive law. Okay. Right? And this Venn diagram shows this property for the sets. So if you take the union of B and C and then intersect with A, then that's just the part inside A, which also inside B or C, right? Okay. So the shaded area in the diagram. And that is actually equal to the intersection of A and B union with intersection of A and C. Okay. All right. So we all know that. Okay. So that's one way you can use Venn diagram, and you can also use the algebra properties we just discussed, as we're going to see some examples later. But there's another way to do it. You can also, prove this kind of inequalities by the previous techniques, using the sets. If you pick up any set on the left, I mean any element in the set on the left, and then you just prove that's also a set on the right side and then vice versa. Then you can prove these two sets are the same. So, for example, if you try to prove the last equality, A intersecting with B union C on the left equal to the A intersecting B union with A intersecting C. We can use the proof technique of sets for sets. So just take up any arbitrary element on the left hand side set. So which is A intersecting B union C. So that means X is in A and also X is in B union C. In other words, X is either in B or X is in C. Okay, that's what it means by union, B and C. So then we have two cases, either X is in B or X is in C or both. But we just need to consider two cases, X is in B and X is in C. If they are in both, then that's also included in those two cases. Okay, let's see what happens then. Okay, so suppose X is in B, then what happens? And then the other case is X in C, and what happens? Okay, so remember X is always in A, right? On the left-hand side, X is in A. It just splits between B and C. Okay, so well, if X in B, but because X is always in A, so then X is in A intersecting B. So X is in the union of intersecting B and A intersecting C, of course, right? So that's first case. The second case is X is in C. Then again, X is always in A and X is in C. So X will be in A intersecting C. So of course, X will be in the union of X, A intersecting B and A intersecting C. So if we combine these two cases, that means if X is in A intersecting B union C, then it means you know X is obviously in the union of A intersecting B and in A intersecting C. Right? In both cases, we have the same conclusion here. All right. So so then that means A intersecting B union C is a subset of A intersecting B union A intersecting C, because any element you pick up from A intersecting B union C will be also in the union of A intersecting B and A intersecting C, right? So that's just part of this. Okay. So then if we can show the backward, the reverse, then it essentially tells these two are the same. Okay, right now we only have one set inclusion. Okay, one set inclusion, or one-way inclusion. You know, so this diagram shows if you pick up any elements in A1, it's also in A2. So that means A1 has to be a subset of A2. All right. So let's just show the converse. So we want to show if X is in A intersecting B union A intersecting C, then we have to show X is also in A intersecting B union C. Okay. Well, what it means by X in the union of A intersecting B and A intersecting C, that means either X is in A intersecting B or X in A intersecting C, or both. But these two cases will be include the case of both. Okay. So case one, if X is in A intersecting B, then of course X is in B, right? So X will be in B union C. All right. So but because X is in A also, so that means X will be in the intersection of A and B union C, right? So that's the first case. Or if X is in A intersection C, then X is in C, and so X will be in B union C. But again, X is in A, so X will be in the intersection of A and B union C. So in both cases, we have shown X will be in A intersecting B union C. So that means any element you pick up from this union of A intersecting B and A intersecting C, it will be in the set of A intersecting B union C. So that means the former is a subset of the latter, right? Okay, so then we just prove the the other way inclusion, right? Okay, so if two sets contain each other, then these two sets have to be the same. All right. So we have shown A intersecting B union C is a subset of A union B, of the union of A intersecting B and A intersecting C. And we just showed that the converse, that means the union of A intersecting B and A intersecting C is also a subset of A intersecting B union C. Right? Okay. So then these two sets have to be same. So that's another way to show they're the same. So you can also use the techniques in sets to prove it. So that's the original way we used, not new to us. Any questions at this point?
No, I don't have any questions so far.
Okay. Yeah, I don't think it's complicated at all anyway. So let's just look at one example. So we want to show the complement of the union of n sets from A1, A2 to AN is just the intersection of the complement of each of those sets. Okay. Uh, Again, we can use the same strategy to prove it. So you just pick up any element from the set on the left. So let X be in this complement of this union of n sets. So what it means is X will not be the union of A1 to AN. That's what it exactly means. This X is in the complement of this, right? So it's not in this union, but it's outside the union. Okay. So that means so X is in none of those AIs. Okay. Because if it is in one of the AIs, then it will be in the union of those n sets, right? So X will be not in any of those AIs. Or it has to be in all of the complement of AI. If you think about it, it's not in. So for any specific AI, X is not in it. So X has to be in the complement of AI for each eye, right? Because this is true for all the eyes, for any eye. So X has to be in the complement of each of those sets. So that means it has to be in the section of those uh, uh, complements, right? And this argument goes both ways. All these arguments are equivalent. Okay, if you just think about it, they mean the same thing. When we go from step to step, each time we do, we can go both ways. We just uh, make equivalent statements. If you remember what we did in the logic. Any questions about this example? So this is basically using the definitions uh, of the sets and the complements and some logic. Okay. So then we showed the complement of a union of n sets is the intersection of those complements. Okay. Well, you can actually use the same argument to show this union up to infinite many sets. Okay, so the difference between this statement and the previous one is the previous one has finite number of sets, right? And here we have infinite many sets, but the argument is the same. You can use the same procedure to show, the union of infinite many sets, the complement of the union of infinite many sets. It's just the intersection of the of each of the complement of each set, right? And similarly, the complement of the intersection of n sets is the union of the complement of each set. Okay, I think these arguments are pretty, similar that can be done in the same process and same steps as we did in here. So we're not going to repeat. Okay. And you can also extend the statement to infinite many sets. The complement of infinite many sets, the complement of the intersection of infinite many sets is actually the same as the union of the complement of each set. And these equalities are called the De Morgan's laws. I think you learned it before, from 1.2.3 to 1.2.6. Okay. So, when you do the complement of intersections or unions, it just becomes the union or intersections of the complement of each. All right. Okay. So I just said, there are some Boolean algebra similar to the numerical algebra, but not all of them. Some of them are different. So what are the same? The commutative law, associative law, and distribution law. Both are true. But if you look at the Boolean algebra in here, some of them are not exactly the same as numbers. So, for example, if you take the union of one set, you get that set again, but that cannot be changed to a number plus this number itself equals the number itself, except for 0. Okay, so this is not generally true. So that doesn't hold for numbers. Similarly, as a set intersecting to itself, or just the set itself. Again, this is not always true if you change to numbers. A number multiplied by itself, we get a number back. That's only true for 0 and 1, but not for other numbers. So that's not generally true. And any set intersecting with the universal set or the sample space, or if you think this A as an event, okay, there are just sets. It's just the set A again or event again, but you cannot change these numbers and modification and get the same kind of equality. You even don't know what it means by this sample space in numbers, right? And also, if you take the union of a subset A with the universal set, you get a universal set. Okay, so this is not true for addition of numbers also. Okay, and these we can, it's not strictly true mathematically. Okay, if you change these two numbers. But some of them still are true, okay? Like A union A complement equals the universal set or the sample space. You can actually write addition, of two numbers to get a total, okay? And this A intersecting the complement of A is obviously the empty set. That one is hard to find the correspondence in numbers, okay? you multiply a number by another number, you get 0 or whatever. But this one, a unit with empty set is a in terms of sets or events, you can change these numbers, plus 0, you get the same number. And the last one, a intersecting empty set, you get an empty set. If you change a to a number multiplied by 0, you get 0. So some of them will be true in numerical algebra, but some of them are not. But we can still use those properties, these equalities, in the Boolean algebra when we try to prove some results. Okay, we use these results instead of numerical correspondence, which do not exist for some of them. Okay, and let's just use that to prove Boolean algebra. So this is something I don't know if you learned before, but it's interesting thing. Okay. So this is another method. Okay, is in addition to the method we just talked about using the sets, pick up an element in the sets and then try to prove any element in one set is also in another set, and vice versa. To prove these two sets are the same. Here we just use the Boolean algebra itself to prove it, and it's very simple. It's much simpler. Okay. So you can use the identities with distribution law, commutative law, and associative law, which is true both for numbers and sets, so that we can interchange the symbols for from the sets to the numbers and using the same laws. Okay, and for some other properties or identities which are not true in numerical algebra, we can still use those identities in the proof. Okay, we can still use those identities in the proof in Boolean algebra. So for example, let's start from a simple example. You can see how we can proceed with it. So the key is you change the unit as plus and the intersection as multiplication or nothing. Okay. So for example, if we want to show that a unit with a intersecting b equals a itself, then if you change the unit to addition and intersecting as multiplication, so then we get a plus ab on the left-hand side. And because those three laws, the associative law, distribution law, and the commutative law, applies both for Boolean algebra and numerical algebra, then we can do the same way as numbers in Boolean algebra in terms of those laws, right? Okay, so then we can use the other identity, which is not true in numerical algebra, but it is true in Boolean algebra because we're trying to prove, algebra events. So you can write A as A times omega, which is the universal set. Okay, that's actually this A times omega equals A, or U intersection, right? Change to times. So you can write A as A times omega. Okay. So, and then you can factor out A because distribution law is true both for Boolean algebra and numerical algebra. Then now omega plus B is just omega, in terms of sets, right? Omega plus A is just omega for any A, right? If we change the unit to plus. All right. So then we got A times omega, but that's also A. If you look at this, A times omega equals A. Means intersection. Okay. So we just write it in this way so that we can handle this loss, 3 loss, in the same way as numbers, but we should always understand them in terms of union and intersection. Okay. So at the end we get A equals that on the left. So we prove it. Very simple, right? So I guess it's time to stop in here. We're going to finish this section next time. Any questions?
No, I don't have any questions.
Okay.